Okay, welcome to Learning Target 5, Hypergeometric Distribution. This is actually not anything really new. We've done this before, and so you'll find out pretty quickly. We just haven't done the expected value. This really builds on what we've done in the second unit. So warm-up here is your class is 8 males and 11 females, and 3 are being chosen for a dangerous mission. Well, what is the probability distribution formula? P of x if x represents the number of females chosen. I can't imagine the dangerous mission that a teacher is sending a class on, but this is, I guess, just to make it a little bit exciting. So like what we're looking for is you want to ask yourself like how many different females can you actually get, and we want basically you might want to start by trying to figure out what's the probability of each of those. But then we have to make an equation based on the general case. So where it's just x represents the probability number of females chosen. I'd encourage you to try this. I'd encourage you to pause it and try to write this down on your own, just so that you can see exactly how you would do this. So learning target is I know the hypergeometric formula gives me a way to calculate the probability of different outcomes where order does not matter. It is used when the trials are dependent and we're counting the number of successes. I know that the expected value can be calculated relatively easily by multiplying the number of trials by the probability of success in the first trial. This is going to be very similar to the binomial distribution, and in fact we'll spend the next unit just talking about the next lesson just talking about the difference between the two and making sure we choose the right one. But the ones we see today in the practice are going to be hypergeometric. So this order does not matter. It might start getting you to think about how we actually do this. And if you kind of went through with the warm-up, you'll notice that we use combinations for this. Trials are dependent actually means that like if we pick if we pick 3 females, after we pick 1 female, the probability it does change. And what it changes to is what we call the conditional probability in the first unit. But it's just the idea of combinations, and really that's what we've been doing when we do combinations. So the probability of x represents the number of females, so you can have 0 females, 1 female, 2 females, or 3 females. And so we make a chart, and it's really helpful to draw the chart, and then that way, like no matter what you're being asked for, based on the number of females, you can answer the question. So the probability of 0 is 11 choose 0, so 11 females, we're going to choose 0 of them, and 8 choose 3, which is 8 males, we're going to choose 3 of them. You might have just said 8 choose 3, because like you don't really have 11 choose 0, it's just one way to do that. But this is going to be for completion, much like the binomial we did. So probability is actually just under 6%. Probability of 1 is 11 choose 1, 8 choose 2. Over 19 choose 3, it's like 32%. Probability of 2 is 11 choose 2, that's 45%. The probability of 3 is 11 choose 3. We don't need to say 8 choose 0, but we do just for completion. 17% chance of choosing 3 females. What you could expect is a bit higher. It's actually a lot higher than choosing 3 males. Even though you just have 11 females and 8 males, that makes sense that it is dramatically higher, but it's actually 3 times higher, even though you just have 3 more females, which is not really that important, but it's interesting. If we multiply x times p of x, we actually get the expected value. So we're gonna work on that. We just multiply the numbers together. When you add them up, you actually get the expected value. So the expected number of females we get is closer to 2, 1.74 on average, but that just means that it's really more chance of getting 2 than it is of getting 1. If we try the expected value formula from the binomial, we had something like n times p. N is going to represent something a little bit more than the 3 in this unit, but we're just gonna, or in this lesson, but we're just gonna pretend we do 3 trials, so we pick 3 people. So if we multiply 3 by 11/19, the probability of getting a female is 11 over 19. If we had to say the probability of a female, that's only in the first trial, but we try that and see what happens, and actually it gives us the exact same thing. And so this is going to be our formula, a little bit different. We're going to call it RP, but a little bit different, but it's going to be very similar. Okay. Hypergeometric formula and expected value. I changed that to RP from NP because it really just makes more sense. Like we don't want to call N something different. So this is the formula. I don't really like it. You just really have to understand like what it looks like. Like this is like 11 and 8 added up is 19. 1 and 2 added up is 3. 19 and 3 is like the total and total number you're choosing. These are like the subsets, like the two categories. In hypergeometric, just like binomial, there will always be two categories. Even though in the second unit we saw combinations where you had 3, probability of combinations where you had 3, or more. In fact, on the unit test, we did like 4 categories or more. And so, but like here we just see 2 categories: male or female, success or failure. That's what just like the binomial would have just 2 categories as well. 2 variables that have exponents. These are just 2 combinations. A plus n minus a actually adds up to n. X plus r minus x equals r. This is a little bit easier to understand if you actually do it in an example than just looking at this general formula. This really looks kind of ugly. X is the desired outcome, like 0 females, 1 female, 2 females, 3 females. A is the total number of desired outcomes. So like we want 0, 1, 2, 3. Like how many females there are total. Total number of outcomes there are is the 19, and then R is the total number being chosen. If we multiply the total number being chosen by the probability of success in the first trial, we actually get the expected value. Very similar to the binomial. It's not 19 times the probability, and the probability is not as clear, but that's why we say the probability of success in the first trial. These formulas you'll be given, but really I think that it's just more helpful to understand the combination. Notes on hypergeometric. We've seen this probability before when we use combinations. Trials need to be dependent where the probability changes after each selection. We'll go on a little bit more about dependent and independent next lesson. So an example was a probability distribution table for number of hearts. If you select 5 cards from a deck of cards, and what is the expected number of hearts? So actually here we actually went through just want to show you the spreadsheet that was used to do this question. And so this spreadsheet was used to do it, and I'm just going to zoom in on it so you can see a little bit better. So this is the probability distribution for the number of hearts if you select 5 cards. You get 0, 1, 2, 3, 4, 5. The spreadsheet really helps to do the probability because like we can actually enter this formula combin. If you're not familiar with spreadsheets, you just have to press equals before. You can press combin 13, choose the reference cell, which is 0. And really, if you're typing this in yourself, you would really just say you would just like click on A10. You don't have to type it in. The 39, which is the number of non-hearts, we're going to choose 5 minus 0, so 5 of them. The reason why we don't just type, like you could just press 5, but like we're actually going to do this 5 or 6 times, so it helps just to copy and paste after that. And then it's divided by the combination. I just use brackets to make sure that I multiply those first. Although like Excel will use BEDMAS, and we divide 52, choose 5. The benefit of using the reference rather than just typing 0 and 5 is like you can take this little blue dot here and drag it down, and it'll actually fill, and so that the reference changes. And so like for this one, for example, it would be 13, choose 4, and then 39, 5 minus 4, which is 1. And that uses the formula, it's 1%. The benefit to this too is like you can quickly do the expected value just by type equals that times that, using a little star as times, hitting enter, and then pulling it down, and the reference will go down as well, and we quickly get the expected value as the sum. Just type equals sum. So if you don't have this, equals sum, and then highlight it and hit enter. And so like we can actually very quickly get the expected value and also the probability of every outcome. What this allows us to do, let me just go back to the correct one. Got all these tabs open. What this allows you to do is really quickly answer questions like, what's the probability of getting 2 or more heads? They just add these up. Probability of getting at least 1, just add these ones up, or do 100 minus this one. We could do the probability that if you get 5 or less than 3, you can just add these 3 up. So you can ask her a lot of questions in that case. That probability does use that formula. So this is the general formula. 13 choose X, 39 choose 5 minus X. The expected value is 5 times the probability, because 5 cards are being drawn, times the probability of getting a heart, which is 1/4, and we get 1.25 hearts. I made this little symbol. The math type has these little symbols for the different suits. So if you ask a question like, what is the probability that you have a hand with less than 2 hearts, you can just say, oh, it's going to be 63.29%. We just add up the 2 that we get, and we get 63.29. So that's it. You can try these questions for practice.